Hello everyone, I'm Jason Sykes, aka the Tech Rancher, and this is my homework solution for lesson number 40. This is a course brought on that's taught by Paul Mcwhorter. It's called Raspberry Pi Pico W. You can check it out on YouTube and by searching for Paul Mcwhorter, or you can look at his website at toptechboy.com for more information. Enough about Paul, let's get to the homework solution. Alright, the homework solution was Paul had asked us to measure the z-axis and predict what the value would hold or would be by setting still. If it's different, then explain why it was different to the best we could. Alright, my prediction is it's going to be 1G. It's because we have Earth's gravitational pull on us at all times. And so I think this thing is going to be able to read it. Now, I'm not for sure, but we're going to find out. Alright, let's take a look at the code and see what I did first here. If we want to go ahead and start right here, I imported the libraries. It's our normal libraries that we imported. The only thing that we did differently is we have to include a library called MPU 6050, and no, it's actually called IMU. Sorry, the library is called IMU, and the class that we're using is called MPU 6050. When you import it, I downloaded it off of GitHub on the SunFounder Kepler. When you go to type in SunFounder on the search bar in GitHub, but it needs to be SunFounder / Kepler. Then you want to go ahead and download the library system. I don't have it included in here because all I brought in was the IMU. But once you get that, you need to access your Pico W. If you're using Visual Studio Code, the way how you get that, and if you're using the extension MicroPico, which I was going to try to pull it up here real quick to show you. Let me type it in. Oops, whoops. M-I-C-R-O. If I can spell, y'all. That's one of my biggest problems. There we go. Now let's type in MicroPico. There we go. If you're using the MicroPico, the extension on it for Visual Studio Code. Now let's go back over here. If you're using that, which I'm of course I'm using it. Then let me close it out. Right over here, to be able to get access to your Pico W, right down here in the bottom, at the middle of your page, down to the bottom, it says Toggle Pico W. If you click on this, this will actually, which now it's just going to redo it all here. Let me click on it again, but then it actually pulls up your Pico W all here on your side where all your tree is. And if you click on your tree, you'll see a lib folder. I know Paul in the video had mentioned libs. I did read that in one of the documentaries. That's why I wonder where Paul came up with that for the libs, L-I-B-S. But when you use Phony and you download a library in Phony and have it put into the Pico W, it creates a lib, L-I-B, instead of an L-I-B-S. My very first one was the SSD, the 1306, and I used that through Phony, and before I figured out how to do it through the Visual Studio Code, sorry. And now I just go ahead and I just do it this way by toggling in the Pico W, and it gives me access to it. Then I can go into that library of lib, and I just dragged and dropped the IMU into that. As you can see, you can access any of the files on your Pico W through the VSC, and it shows you right here on the sides. And then this is what it would be, that library. It's a very extensive library to be able to run and grab the data that this beautiful piece of equipment makes. And it's fascinating to learn that Paul was one of the first pioneers that helped come up with this concept of being able to collect data from accelerometer off of a silicon silicon chip. You know, that is mind-blowing. I mean, that is minute, tiny, and my hat's off to you, Paul, because that's some smarts. All right, enough about that. Let's get back to this homework solution. All right, here we are. We got our libraries. We imported our libraries, and we're importing all the basic things that we normally did, and we're also including that, what I said, IMU library with the, and we're grabbing the class of MPU 6050. Then we imported time. Now we're setting our variables. I like to use const. You can use whatever you want. I just like const because therefore they don't change. It's a little bit of the C++ inside me that is sticking there. Okay, anyway, I set my variables for that, and I broke them up so I could be able to read it better. And once I got that, I went ahead and created my objects. And I'm using the Paul said to go ahead and hook up in the video for lesson number 40. He said go ahead and hook up your OLED and the SSD 1306. And so I will show you the schematics here just in a little bit of how to hook that up. And so I went ahead and thought, well, if I'm going to hook it up, I'm going to go ahead and use it. I know how to use it. So here I created the object for it. And then I went ahead and created the object of our MPU 6050. And then I have my function that I normally do for when I'm using the SSD. And it's my center text function. And then we're going to put everything into a while true block. Now I'm getting ahead of myself too a little bit fast. Some people might not even have this hooked up and they want to know how to hook it up. So let me get over here and get that brought up for you guys. Bear with me. There we go. Hey, we got it right here. Alright, I should have done this at the very beginning, but here I am doing it now. So here's our OLED and then our MPU and our Pico W. We're going to take the main power, the 3.5 coming up for the power rail on top. I know some people like to drop it all the way back behind here out of the way, but I'm just going ahead and crossing right over my Pico W and powering the power rail on the top, and then I'm grabbing my first ground on the opposite side and attaching to it. Then we're going to take our first, we're going to grab our SDA off of this pin right here coming off. I'm going to make sure I know what pin it is, so if you're looking at that, you'll see that is going to be pin 2 and pin 3 are those two pins there. So let's minimize this here. So then we got pin 2 and pin 3, and then pin 2 is running here for our SCL, and then, or actually no, SDA, and then SCL is running off pin 3. And then we're grabbing our power off the power rail and ground off the, ground and then power. Mine's reversed. There's two different styles of this SSD. Mine is power first, then ground on the outside. Okay, then we go back here, and then we're grabbing for the SDA and the SCL. So let me pull that back up here. And pin 13 for the SCL and pin 12 for the SDA. Bring that back up. And so you can see over I'm running for that 13 coming over here and running in for the SDA, and then 14 with the white one coming down here for the SCL. And there you go. We got it all hooked up. And that's what will allow the code to work. So let's back here to the code. Okay, so we got all this code pulled up, and now we're in here to the while true block. I'm going to use 3 variables that are going to hold the value of from our accelerometer. It's I'm using X cell, Y cell, and Z cell. A cell. And then we're calling in the library MPU, and then using excel.x, y, and z. These are going to read the values coming off the accelerometer. And then I got the code here to be able to display for the OLED, and then printing out here, you can print out on the screen, which I'm actually printing on the OLED, but here on the screen from when I was doing my testing was right down here also. Now let's pull up this display and let's get it started. I'm going to go ahead and hit run right down here, and there you go. You can see it started up and running. And that is about as good as I could for zooming up. Let me try this a little bit more. I don't think it's going to work. Yeah, hey, there we go. Okay. You can see right down here that our z-axis is reading 0.92. My prediction was pretty darn close. If you just pretty much think about it, we got ground, we have gravitational pull down upon us within about 1G, always pulling down upon us. And so that was why I predicted at least 1G. I did not know if the accelerometer would actually show it. So when I was getting my homework ready, I made that prediction, and I wrote my notes, My notes. I wrote my notes, and I actually wrote in my notes before I even started the code that it's going to probably be at least 1G. I was hoping, and it did. So after I got finished my code, I launched it, and I saw down here in the very bottom that it was 0.9, and it was something like 0.94 or something. So hey, I got it. Now, Paul goes underneath the hood and explains how that works, and I cannot do justice for it. A lot of the math went over my head, but Paul does a really great job emphasizing the significance of understanding this, and I got a grasp of it, how it works in my mind, but for me to be able to take that from my mind and to translate it into communication for you to understand probably won't work very well. But I just know it's floating above the silicon wafer, or as it's processed, the silicon, and then it's floating above it with springs helping hold it up. And a distance from that silicon to the plate is what we're wanting to read, and we're using capacitance to be able to determine that. And then since it is already on a silicon processing, we can use electronic gates, logic gates. We can use different logic gates to take this information from that and have that do the math for us. Wonderful thing about technology is that it does things to make it easier for us, but in a way it makes us dumber. That's why I'm trying my hardest to get a grip back onto math that I've lost for almost 30 years of not using it, high advanced math. So let me look back here on my notes and see if there's anything else I need to address. If you want to get a really good understanding of it, check out that lesson number 40 that Paul does. Paul does a great job explaining, and if you have a good understanding of math, you could probably be able to understand what he's trying to explain to us too. But I was appreciative of his drawing because I'm a visual learner, and that helped me be able to lock it in. And then I know that delta is the change in delta of the distance, and the change in delta of well, see, once again, I'm going to try to explain it, and I'm going to mess it up. So I'm not going to try to regurgitate what Paul had taught in that, because I will mess it up. But check it out. You'll learn a lot. And in the process of that, Paul is also trying to just show us how awesome this accelerometer is. This one's a 6-axis accelerometer. It does all 3 axes of the acceleration and all 3 axes of the tilt. And we're going to be getting to tilt a little bit later on here. Well, I think that I did as good as I could to try to explain this for the homework lesson. Oh, well, I mean, other than, showing the g-forces being applied on it for moving it in the x-axis and then moving it in the y-axis, because I knew I was not going to be able to display it very well with my camera the way how it's positioned. But you can see in my display down here below that it does move. I can pull it up a little bit. You can see that we do get a reading in our y-axis and do get a reading in our x-axis when I'm moving this down here at the bottom down here. You can see that at the time we were at 1, now we're coming up and reading up higher than that, and then we come over here and you can see that we're reading higher than that on our y. And in our z-axis, if I do a little drop, you can see that we're reading the indication on that too. If you have any questions or comments, leave them down below. I'll do my best to try to answer them with the knowledge that I have. And until next time, be safe out there, everyone.